Thank you very much for the opportunity. It's a great audience, and I think I just killed the clicker here. I'll see if it still works. I think the last two talks almost perfectly set up this talk to explain why very large data sets right now reside in cloud. And because they reside in cloud, the challenge that we face in scaling the cloud infrastructure that in fact supports that data set, right? So that's what this talk is going to focus on. Great, it still works. So many of you have seen what Google's mission is, and this is the mission on which the company was founded on, and it is still our mission, which is to organize the world's information and make it universally accessible and useful. From the infrastructure point of view, this mission statement makes it an extremely challenging job to scale our infrastructure to meet this at the rate at which the internet is growing. And here is an example why that is. Everything that we do is about scale. And if you look at the scales that we're talking about, the world population is somewhere around 7 billion people. This is a bit dated data. The internet users are getting closer to about 2 billion. We serve more than a billion queries every day. Geographic distribution, it's a worldwide service, right? So our services are over 55 countries and 112 languages. More than 50% of our search queries actually come from outside of the United States, right? Data growth. The data growth has been explosive in the internet. On an average, billions of new modified pages are added in the internet. So in order to go and index it on an hourly basis or several hour time scale, we go and crawl the whole internet and gather more than the whole of Library of Congress in terms of the data that we go and collect. You have heard of a small site called YouTube where you go and watch video. Every minute, users upload 24 hours worth of video to that site. And much of that is actually in HD today, thanks to the easy access to HD video recording devices, including your phone, right? And of course, with that and being a global service, you have the obvious latency challenge, right? Bits don't move faster than light. And therefore, in order to provide users with information or answer to their queries in a time scale where the users don't perceive that they're waiting for the answer, which happens to be less than a second, you need to do something very specific in order to scale this infrastructure so that you are not killing latency in the process, right? So you have to address the latency issue as well. And one way that we found of answering a lot of these problems is by building our infrastructure specifically to scale to meet our users' need. And we do that by building something which we call warehouse scale computers. I'll go in a second as to why we call them warehouse scale computers and not data centers. There are some very, very distinct differences. The goal, though, is it goes back to what my previous speaker talked about, which is there are really two things that are happening when you're computing today. There is a visual part of your compute, and then there is a compute part of your compute. And that compute part of your compute doesn't need to happen on the device that you're using to access that. However, you should have similar experience whether you're on a phone, whether you're on a laptop, or whether you're on a tablet device, right? This is exceedingly important because people are accessing compute resources with devices that are not necessarily the highest performance devices to do compute, right? Your iPhone, for example, again, something that my previous speaker touched upon. In order to be able to do that, you need to build a backend infrastructure which takes the time-consuming part of compute away from the device that you're using to access it. And in order to do that, the way we do it is, again, what we call warehouse scale computing, right? And here is an example of a warehouse scale computer that we have built. This is one of our data centers in Oregon, and I'll point out a few interesting things here. One, as you look at it, you basically see two warehouses. They're full of computers. That's the simple reason we call them warehouse scale computers. They're literally a warehouse full of computers. You notice that they're very close to a source of renewable energy. It's in fact really, really close to a hydroelectric plant in Oregon, right? So we're looking for most efficient and renewable and as much possible renewable energy to power these plants because they do take a lot of energy. You also notice these two towers, they're cooling towers. And I'll go into that in a second. They're not your traditional chillers. Chillers are actually extremely inefficient in cooling computing devices. So we have done tons of innovations in getting the energy and the cost, obviously, out of this cooling infrastructure, and I'll touch a little bit on that. So what's the difference between a traditional data center and a warehouse-scale computer? Why don't we just call them data centers? So there are some couple of very interesting differences between them, which in fact leads to the main topic of today, which is energy efficiency. So in a traditional data center, the way it's built is your infrastructure is decoupled from the compute that goes into it. You basically build a shell and core. You come up with a way of cooling, and then you plan to cool certain heat load or certain energy load that you'll have in the data center. And you fill that up with compute equipments that are heterogeneous in nature. They could be various generations. They could be for various different usage. You have storage arrays. You have compute arrays. There could be various different networking equipment to connect them. And since you are designing your infrastructure not quite knowing what compute equipment is going to go into the infrastructure, you are always designing for the worst case thermal load, which ends up leading you to build an infrastructure which is not quite energy efficient. How is that different from the way we do it? In Google's infrastructure, and Google is not the only one, there are other companies similar to us who are building this infrastructure in a very similar manner these days, where the design of the facility and the compute is integrated from day one. What that really means is that we build our infrastructure with utilities that are designed specifically for the compute equipment that goes in there. The same thing is true with cooling. The cooling is built to specifically cool the hardware that is going to go into that infrastructure. The flip side of that is the hardware is designed to be completely optimized to go sit in that infrastructure so that you get the best efficiency out of both. And that has huge value in terms of both energy efficiency and the scaling that you need to hit. So simplistically, how does this work? How it really works is if you go and walk into this data center, you're going to go and see rows and rows of exactly identical looking compute racks where the individual elements are really off-the-shelf computer with some modification that we do, and I'll go into that as well, where we do the modification. But these are really commodity hardwares. The commodity hardware, they're stacked up on racks with a set of switching equipment that basically helps you connect these devices or these servers, individual servers that go in there. They're then arranged in rows and columns of racks which are combined into a cluster, and they're connected by this cluster networking gear, right? So simplistically, that's all it is. However, there are a very large number of them. And as a result, they consume a large amount of power. And I think you heard before that if internet was a country, it would be the 5th largest consumer of power today. It's right behind Japan, and it's right above Russia, right? The point is that it's not just Google. Most of the large internet service companies build their data center in a similar manner because of the nature of data that you're actually processing. It's a very large data set, and you can process that large data set only with a certain type of infrastructure, and this infrastructure is here to stay. It's not going to go away. What it really means is that you need to do everything that you can in order to get the most efficiency out of this class of compute infrastructure that we're building, right, or various people are building. So one way of measuring efficiency in data center, and this is a method that EPA has used, and they have some roadmaps on that. It's called PUE. It's the power usage efficiency. And the way it's defined is the ratio of the total facility power divided by the power that is being used by the IT equipment. So a simple way of looking at that is if you look at your desktop computer at home, the PUE is actually more than 2, which basically means that if you plug a desktop computer into an outlet in your home, more than 100% of the power, or rather whatever power you use in the computer itself, you waste almost the same amount of power in various places, including utility lines, the way the power is converted inside this equipment, the way the equipments are cooled. Some of that comes from the air conditioner that you run at home to cool this gear so that it doesn't overheat, right? The industry average of a generic data center, and this is a generic data center, this is not warehouse scale computers. The industry average of a generic data center is slightly better than that, but not terribly better than that. It's about 1.9. There's an EPA target of 1.2 in 2012 for the state-of-the-art data centers where everything has been done in order to get the most efficiency out of the energy that goes into the data center. This is something that Google has been spending a lot of time, energy, resource, and research on since the inception. I mean, that's part of the reason that Google's infrastructure went into what we call warehouse scale computing, and it is not done by traditional data centers. These are graphs of some of those, and I think goes back to 2007, I believe. There are a whole bunch of data centers that are plotted here. What you'll notice is that all of them are less than 1.3 PUE. We have come pretty close to less than 1.2 for all the data centers, and you're seeing many generations of computers and machines and other infrastructure that are in there, right? The key thing here is that we can say that compute is getting more power hungry because we need more and more number of those. There are certain things that are constant, which is how you design, how efficiently you get power into your compute mechanism, and there are a lot that you can do in order to make it efficient. This is a graph of one of our newest data center, where what you see is that we have actually hit less than 1.2. So really the way to read this is you waste, if you were to use 100 watts of actual compute power that goes into your computers where it runs the computer itself, you waste about 16 watts of power in that, which is, as compared to the industry average, it's 90 watts. So you've actually taken out a significant amount of power. There is another very interesting aspect of that, right? So you have often seen this alarmist view of, internet consumes this much power. Well, the truth is that compute in general consumes a lot of power. The more people are using high power compute, the more power they consume. If they're doing all that computing at their home computer, they're actually consuming a lot more power than if a lot of that processing is in fact happening in cloud, for two reasons. One, like I said, the home computers are actually not terribly efficient devices. They're in fact very inefficient. The second problem that you have is that because there is no statistical multiplexing of processes that are running on those machines, you're wasting significant amount of energy in spinning hard drive or running screensaver on your machine where you are still draining it from the grid. While in these cases, since these servers are multiplexing a large number of compute process in the data center, the amount, the 100 watt that is actually going into these machines are real 100 watts that are getting converted into compute. So if you do a global analysis of how much power efficiency you get by processing this large data into the cloud infrastructure, you actually have gain in two places. You have better efficiency in this cloud infrastructure, and you have better efficiency in how you use the infrastructure itself in terms of getting useful compute out of it. You remember in the first picture, I showed you a picture of this, which I call cooling tower, and I mentioned that it's not chilling. While designing these warehouse scale computers, we realized that chilling is a terribly inefficient way of cooling this equipment. That's where WSCs are different from traditional data center. In traditional data centers, you design them for generic equipment that you don't know from day one how they're going to look like. So you go and design them with the traditional way of cooling, which is more often than not chilling. These data centers have been designed for specific hardware, where there are specific designs with how air flows, how heat is taken out of these devices, right? What we did is we went and built, in fact, this is a significant invention that Google did. We built these cooling towers where what they are, it's very simple in concept. You basically run water around your servers. It uses as a heat exchanger. It takes the heat out of the servers. You get hot water that is pumped up to the top of this tower. It's run through a specially built tower where this is basically built with a special set of a special type of material, which allows this water to evaporate very efficiently. As the water evaporates, it takes latent heat out of the remaining water. So the water cools down as it's going down. At the same time, you have this fans. This fan is basically sucking relatively dry air from the environment, and it's pulling it up. So it's taking the moisture out of the evaporation that has happened. And in the process, you basically have cooled the water, and then this water goes right back into the data center. So good. We've taken a lot of the cost of chilling out of the process, right? But fresh water itself is also very valuable, right? So it consumes energy to get fresh water. So what we do is we use recycled water. So what you're seeing here is this massive recycling plant that we have built within the data center, where I think one of the audience member had a question before where, the question was, how do you really marry your utility grid and other infrastructure to the data center? We actually are doing it today. It is done in a way that you are not wasting the energy of the utility in doing that outside and bringing it back to the data center. I'll give one other example that I have done, which is very interesting in this context. The latest data center that we announced that we built in Finland, it's built in a place which is around Gulf of Bothnia, where your average water temperature around the year is less than 40 degrees Fahrenheit. We don't do any cooling there at all. We use the water directly from that Gulf, the Gulf of Bothnia. We run that through the same system. We don't even need to evaporate because the water itself is cold. And we run it around the server to cool it down. So you have completely eliminated the cost of chilling. And that's how you're getting to a PUE very close to 1, where every bit of power that's going into your data center is actually getting used for useful compute. In addition to that, we actually have spent significant amount of time in building servers that themselves are energy efficient. How do we do it? We do it in multiple ways. We have taken out elements that are seemingly common in data center but can be very energy inefficient. UPS is a great example. When you have a common set of backup battery which gets charged and it may or may not get used and it's discharging, you're actually wasting a lot of energy in the process. What we have done is we have completely eliminated UPS. We have replaced them with small batteries that go on the servers themselves. So as a result, you have the small units that get charged, that gets charged or discharged if necessary, and you don't have the cost of distributing this backup power across the server floor where you waste energy. We have also eliminated, you may remember that I said that these things are built with commodity hardware. They look like standard motherboards, Intel or AMD based standard motherboard that you find on the market. What it did do is we eliminated all the components that are not necessary for what we do. Graphics chip is a great example. We process graphics. We don't produce a graphical rendering of the output, right? That happens in user's device, and therefore we don't need any graphics chips on the servers. We have completely removed that. We have optimized the fan speed. Fan is a killer waste of energy on your servers, and you can do significant optimization in how these fans run. We have optimized fan power. The goal really is energy proportionality. I'm almost out of time. I'll basically leave you with this one last slide, which is kind of similar to what many of my, actually both of my previous speakers pointed at. The new Moore's law, as we talked about before, is addition of cores. It's not scaling of the clock speed, which works great for what we do. This is again something that my previous speaker pointed upon, right? This is the data set that we are actually dealing with. So parallelism works extremely well with what we do. The problem though is that Moore's law has allowed us to get to higher number of cores without increasing the without costing us too much more. We do need more and more compute in order to scale the way our services are, which essentially means that the proportional cost of energy as opposed to compute is growing by every day. So what you really need is energy proportional computing, where in fact it's not only just the cost of compute, but the power consumption that it takes in compute to go down as we grow in terms of efficiency and the ability to compute more. So there are a few other things that are interesting with this large-scale data center. Networking is a very interesting piece of it as well, where it's important to get the cost out. I would not have time to talk about that today, but I mean there are other places where we talked about that. Energy efficiency is something that as a company we take very seriously. We have spent significant amount of research where we are very interested in working with researchers to get the most energy efficiency that we can get on both our compute platform and our networking gear. So if you have bright ideas, please email me, please come contact Google or anybody that you know there. I'm happy to be a contact point if you have bright ideas there. And thank you very much for listening.